Hello, in this very short video I want to show you how I taught a snake to slither. So, we have the classical game of snake, a game we all remember from all Nokias. We have a snake that has a head and has a body, here shown you in white and gray. And there are apples. We will consider the green apple to be a good apple. Whenever you eat it, you increase your length by 1. We will consider the red apple to be a bad apple, and whenever you eat it, your length decreases by 1. If by any way your length decreases to 0, you die. And if you hit a wall or you hit a body part, you will instantly die, so that's very bad. We have a starting point that is basically played randomly. We can press any of the 4 keys, up, down, left, right, and without any knowledge, the situation looks something like this. So here we can see the agent pressing some keys, moving left or right, and then hitting a wall. It will sometimes find an apple and it will eat it, but it's not usually something it does. It just presses buttons randomly and moves into walls. How are we going to do this? We are going to do something called reinforcement learning. It's something to make the system learn from its mistakes and improve. It learns through trial and error after playing a lot of games, and it has no dataset, only the place itself. What do we want? An agent that considers all informations, and in the end we will see that long-term recoil patterns in the way that it recoils around itself emerge. We have some restrictions. The agent cannot see the whole board. It only sees the head and up, left, up, down, left, right, whatever is in it. Here it is put by symbols. H is head, O is empty, G is a green apple, W is it's a wall, and no memory of the states. If it just saw something the last time and it just moved, it won't remember anything. What we will do, we will use something called Q-learning. In Q-learning, we use a function named Q, hence the name, that it's trying to predict the future. It tells us if we press that button, given the current states, A is the action, A is the actual state, how good it will look. For example, if I press up, it will maybe increase my points in 200 and down in 100, left in negative 100 and right in negative 300. So we will choose up because that's the bad option. And the thing is, this function, we don't know anything about it when it starts, so we start it randomly and we know nothing about it. The thing is, the engine will play randomly, just as we saw. But as the time goes on, we will stop giving the agent random commands and letting the Q function decide where the engine wants to go. Some of the moves will be random, some of the moves will be chosen by the Q action, and we will, as the time goes on, we will increase how many actions are taken by the Q function. So this little oracle that we had, we will update it after each game. So we will say, okay, you're not right, but I cannot throw you out of the window because you weren't right. So I want to do a little update, a little improvement of how you did. And this little improvement is done by this equation here, by the Bellman equation, that says, okay, take whatever you have now and add a little. This little, it's the reward what just happened. For example, if you eat an apple, R is positive. And this gamma, it's a discount factor, some number, so the future isn't always the end goal, but very good part of it. And whatever the maximum of the state that we will end, we will take back. And finally, we will discount the current action, just so this is only the increase. This starts correcting what happens after we we repeat it game after game after game. Remember, a game is 12, 13 plays. Each step is done, and after each session is played, we will correct, and we will play another session, and we will correct, and we will play another session. So, how does that look like? Well, if we load another model, let me check another model here, one with about, and let's see, 100, 100, 100, sorry, 100 dot Keras, and we have here what happens after 100 sessions. We see that it's not that much better than we just had. The agent keeps playing randomly and not even hitting any strokes. So not much improvement after 100 sessions of play. What about 10,000? At 10,000 we start seeing some, not that many patterns, it seems. Okay, it seems like it got worse. What about after 1,000? What about after more than 10,000 plays? Here, this is the best one. And me gusta. Okay, so how does this look? If we train with only one session, here we have a model with only one session, we can see that nothing much has happened. The model just presses down and right, basically, and does nothing else. What happens if we see a model that has 1,000 sessions? Will it be better? It is better, but not by that much. You can see that it tries some patterns. It is trying to hunt some of the apples, but it had some problems. For example, look that it's trying to get to those apples on the top, but it's very afraid of the wall, so it won't go any nearer, and then did a little loop. The model reset because if it has passed about 80 movements without eating an apple, it won't do nothing. See that it has some recoil patterns. It is here recoiling in a certain way just to save space, but it tends to get into big loops. This is a middle model. It has learned some, but not that much. Look that it just entered in another loop, and it will be it'll keep going around until it hits the steps limit, and it will reset again. So, what does a good model looks like? Let's do the best model. This one here. This is the best model. It will actively hunt for apples. Look, that is pointing at the apples very quickly, but it is also, remember that it only looks up, down, left, and right. It doesn't know the whole board. Look that it just said a red apple because it knew it won't matter in the long term. Look that it tries to leave a space at the edge of the board so it can escape if something goes wrong. But it will still sometimes trap himself in the corner like we just saw. This model can easily hit about 30 or 35. Of course, due to variance, it will sometimes do less, but it usually works all right. So let's wait until this finish, and then let's leave some conclusions. So here it is. I hope it doesn't get trapped by himself a lot. Look, that is very, very, very conservative. It values more not getting trapped than going for the quick apple. If especially if things go wrong, here it trapped itself. It did everything he could to escape, but as you saw, it wasn't enough. But just one block. Here, let's close this, and that's it. What did I do to do that? I use Python for the whole game. I use Pygame to do the 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 small game based on squares. The map itself was a NumPy array that I then interpreted as with squares, and the Q function I model with TensorFlow and Keras. I use polars to help me control where each what the snake saw. So the up, left, then right, I use Keras to identify what happened. So that's it, and thank you for being here.